Hi again, and welcome back to the last lecture of this course, lecture 13. After this one, this is it. This is all there is. We are all done. This one is going to be about how to observe the first galaxies, or rather how to attempt to observe the first galaxies, because we haven't actually observed the first galaxies yet. It turns out that this is something that's quite hard to do. But we have made some good strides, and in particular, we have made some, I would almost say, tiger leaps after the launch of JWST. So this is definitely a very exciting and interesting time to be someone who is interested in this kind of question. In this lecture, we are going to take a look at different aspects of how to find the first galaxies. First, we're going to think about, in general, how to design a high redshift galaxy survey. Then we are going to talk something about photometric redshifts. Then we are going to talk a little bit about star formation rates, because understanding star formation rates over cosmic time is really important in order to understand the evolution of the universe in terms of how many galaxies there are, what kinds of galaxies there are in it, how strong the star formation in these galaxies is, and so on. Basically, observing the first galaxy means observing the first star formation, right? Because in the very beginning of the universe's history, that is what a galaxy is. It's a clump of star formation, of probably quite intense and strong star formation. So in order to understand what the first galaxies are likely to look like, we need to think a little bit about what star formation is and how it works. Then we're going to talk about Lyman break galaxies. Lyman break galaxies have been particularly historically, but also they've gotten a bit of a revival with the launch of JWST, have been a method to look for high redshift galaxies in a very efficient and observationally cheap way, which means that we have been able to do this on large scales. Because, of course, if something requires like very long exposure times on very small patches on the sky, then you aren't going to get over a very large fraction of the sky. But if you can find some methods that will help you take very deep images in a short time on very large patches of the sky, then you're more likely to find something that is interesting when you're doing like this kind of needle in a haystack search, which this is. And then we're going to look at a different approach to finding the first high redshift galaxies, which is Lyman alpha emitters. Lyman alpha is a strong emission line from neutral hydrogen, or rather from recombining hydrogen, that has turned out to be extremely effective when it comes to finding high redshift galaxies. But it's kind of hit a wall at this point where it might not be the best way to do this anymore. I'll come back to why and how that is later in the lecture. But first, how to design a high redshift galaxy survey. Typically, such a survey starts with imaging observations, and that's simply because we can get large patches of the sky with relatively short exposure times that way. And then once we have a bit of data, we can start looking at what more specifically we're interested in looking at, trying to select some objects that are more interesting, and then continue on from there. So what we do is we observe a patch of the sky in one or multiple filters, and then we go on to find objects in the images. Obviously, I say obviously, but it's not trivial to do, right? There can be thousands and thousands of objects in such an image, and we need to make sure that we pair the right object in one filter with the right object in another filter, and so on. So there's definitely some work to do here, but from a conceptual point of view, it's very simple. We just want to find all the things in such an image. And after we've found all the things in such an image, we need to define a selection function. We need to figure out what we want to look at, and we need to formulate this in a way such that we can quantitatively pick the objects that we want to look at that seems to be most promising candidates for high redshift galaxies. And there's basically two main avenues to take when we want to do this. The first one is from Galaxy spectral energy distribution functions. We've talked about the spectral energy distribution before, or the SED, right? It is basically like the function of what magnitude we would measure a galaxy to have in various different filters, taking into account various things such as their redshift. And we also need to take into account there's star formation history, the dust, and many other things. But at its core, the SED is quite simple, right? It's basically just a table of numbers. You have like the central wavelength and the limits of the filter. You have the magnitude in that filter, and that's it. And from there, we work on and try to model the galaxies and figure out what their redshift is and what their other properties are. And we'll go a little bit more in depth into how that is during this lecture. Another way we can go about this is that we can, instead of using broad filters, we can use narrow filters. Narrow filters can be very good at finding emission lines, for example, Lyman alpha from before, or H alpha, which is a different hydrogen emission line, oxygen 3, and so on, other strong emission lines. So with a narrowband filter, you need to have an idea of where you want to look, right? You place a narrowband filter, and then you know that if you find something that's particularly strong in this filter, that would either be Lyman alpha at redshift A, or it will be oxygen 3 in redshift B, or it will be H alpha in redshift C, and so on. And so afterwards, you need to work backwards and figure out which ones your candidates are. But it's a very potent way of finding candidate high redshift galaxies if you have a very narrow and well-defined redshift range that you want to look in. We're also going to get a little bit more into detail about that later on in this lecture. A little detour about SEDs. So we want to fit the spectral energy distribution of a galaxy, right? And what we do when we do SED fitting, as we have been through earlier in this course, is that we take our measured magnitudes of fluxes in a number of given filters, and then we construct an theoretical artificial model spectrum based on some physical properties such as star formation history and dust reddening and all such things. And then we basically vary these various properties, and for each of them we construct a model spectrum, and then we basically end up with the model spectrum that best fits these observations, which means that SED fitting can be quite demanding, quite computationally demanding to do. But we also need to take something else into account, and this is not something that's super important for later, but it is a concept that you need to be at least introduced to, which is the so-called K correction. And you can see a illustration of what K correction means in these spectra here, but I probably need to explain that a little bit first. So when we observe galaxies at high redshift, we want to take the measurements that we get, like the magnitudes and so on that we measure, and transform them into what this would say about the galaxy physically, which basically means what this says about the galaxy if we were sitting right next to it and we didn't need to correct for redshift. For example, if we look over here, we can see that we observe a galaxy at redshift 1.5 and we observe it in the H band, right? Then we get a certain magnitude that we have measured there, or a certain flux. We can say here that flux is about a little bit over 4 on this arbitrary flux scale here. And now we want to know what that is in real life, so to speak, what that would be if we observe this galaxy up close. And the problem is we cannot just take this as a right number, right? Because in order to translate this into 0 redshift, we need to also say, so what would this number here translate to if we measured the same value over here, which is about around this line here, right? But there is no filter here. So we need to kind of translate this into a filter we know here or here. And in order to do that, we need to have an idea about what kind of galaxy we're looking at, right? Because the translation from here to here is not the same translation as the translation from here and to here in the blue one. There's also the fact that the filters have different, sorry, you cannot see this. The filters have different throughputs. They're not just like starting like at one wavelength and then letting all the light through and then cutting off at a different wavelength, right? It has some kind of shape that it lets some wavelengths in more easily than others, and we need to correct for this. So we need to know the spectral shape of the galaxy within the measured filter and the filter's throughput. And we also need to know the spectral shape of the measured galaxy at 0 redshift and the throughput function of a different filter that we want to translate this into in order to get actual physical measurements of this. And this requires us to know something both about the filters and about the spectral shape of the galaxy, which we can't always know. So sometimes people have to make do with some assumptions or some very broad hand-wavy models about how that looks. Typically, though, this is not something we have to care too much about in practical life as astronomers, because it is typically often built into modern SED fitting codes. But it is something that is very important to know, that it is something that someone has to care about and make sure happens correctly at some point in the process. And now to an introduction to photometric redshifts, which is not really an introduction, right? Because you have already been introduced to this in the seminars where we have had multiple of these articles that used photometric redshift techniques a lot. But just to get a quick overview, just as these bullet points here, spectroscopy is often too observationally expensive to do for large surveys because there are many faint galaxies and we want to find these galaxies first. This is becoming less true with time, especially after the launch of JWST again, and it's also going to become less true once the EELT, the European Extremely Large Telescope, is going to come online. But it has been a very hard practical limitation on this kind of surveys for a very long time, and it still kind of is. So we often have to use imaging instead of that. And so, as I have talked about before, photometry is basically just like really coarse-grained spectroscopy, right? If you have, let's say, 20 filters of photometry, that's basically like having a spectrum that you have binned into only 20 wavelength bins. So it's very coarse-grained, but it's basically a spectrum, right? So what we can do is that we can estimate the redshift from photometric criteria, from the colors, from the luminosity, and so on. What we do is that we take magnitudes and fluxes in various band passes. The more we can get, the better. And this is, again, what we call the spectral energy distribution. And then we compare them, as I talked about earlier, with various template galaxy spectra at a range of redshift and at a range of different star formation histories and stellar populations, dust contents, and so on and so forth. And then we simply use a statistical technique, for example, least squares, chi-square minimization fitting, or Bayesian fitting, or something else, to find the model spectrum, and therefore also the model combination of physical parameters that best fits the value that we have observed. That is, in a nutshell, what SED fitting is. And one such technique, like the most popular way you can say of doing this, is what we call SPS fitting. That means stellar population synthesis fitting. And that is basically one model of generating these template spectra that you use for SED fitting. So, for example, if we know the redshift for a galaxy and we have multiband observation, we can use these to find the physical properties of the galaxy. As I said before, we have an example here where we have, as you can see, a number of measured fluxes and magnitudes in these broad filters. And then we construct a spectrum, and then we find the one that fits the best. But as you can see down here, we don't just find the one that fits the best. We also try to vary the various properties, such as metallicity, such as dust coverage, various parameters that have to do with the star formation history, and so on. And then we find a distribution. And that distribution gets us not only the best fit value, but also basically an error bar to our best fit value. So you can see that this one has a rather narrow error bar, right? It has a rather narrow distribution. There isn't a lot of star formation, current star formation rates that are consistent with what we observe. On the other hand, over here in the redshift, you can see that there is a wider redshift range that is still consistent with what we see. Still not super wide. This is a low redshift galaxy. It is a good high signal to noise data sets. There's a lot of features you can use to fit. So here we would expect to get a rather nice, neat, and narrow distribution of the various properties. Sometimes with fewer data points, poorer signal to noise at higher redshift and fainter objects and so on, it can be quite messy to look at compared to what we have here. So SPS fittings can be used to, among other things, find the star formation rates, both current but also in the past, through that. Or we can also use what we call calibrated relations, which are basically just statistical relations where we know that there is a large spread, but for example, UV luminosity is a good tracer of star formation rate. So if we can measure the UV luminosity, then we can get a best value of the star formation rate and a certain error bar. The problem with UV luminosity is that it is uncertain due to extinction correction. Dust is quite harsh to UV light, so it can be quite difficult and very model dependent how much you have to correct your observed UV luminosity in order to get the actual physical UV luminosity. And that can be a little bit iffy, but sometimes it's the only thing we have. And also sometimes it's not a big problem because sometimes there just isn't a lot of dust. And the less dust there is, the easier it is to the easier it is to correct for the remaining dust. Then we can get infrared luminosity. This is dust emission from grains. So this is, of course, more reliable if we have a cluster that is like buried deep in big, thick clouds of gas and dust. And it's also better calibrated than UV luminosity, and it doesn't suffer from dust absorption, right? But it is harder to observe, and it has some other problems with various contaminations. But it's a different way you can do it. And then finally, we have a calibrated relation with recombination line fluxes, particularly H-alpha from H2 regions surrounding a galaxy. Basically, the H-alpha line emission intensity is a function of a stellar population's age, and we can that way track that back to the star formation rate of the galaxy at the same time. That is something that has previously been quite hard to do for many galaxies at high redshift, but with James Webb Space Telescope being launched, it has become much easier to do. And it is another one of these techniques that will get a little bit of a renaissance with JWST, I think. We should also note that these different indicators are sensitive to young stars over slightly different timescales. So based on what we will measure, we will also learn something slightly different about these galaxies. We can also learn something about the ISM properties at high redshift if we have emission lines to go with it. We can measure these line fluxes in multiple emission lines, and we can derive a number of physical ISM properties. An example here is what we call the Baldwin-Phillips-Turlowich, or just the BPT diagram, which is a diagram that basically categorizes different galaxies into different types based on what the source of their ionizing radiation is. So what we have here on the y-axis is the logarithm of the ratio of an oxygen 3 line divided by the H beta line. And then on the x-axis, we have the H alpha line and the neighboring nitrogen 2 line at 6584 angstroms. The reason why these lines specifically have been picked is, apart from other things, that they physically are reflective of some physical properties in the galaxies, but also that they are very close to each other. H beta and oxygen 3 are very close to each other in wavelength range, and H alpha and nitrogen 2 are even closer to each other in wavelength range, which means we don't need to correct for dust, because the dust correction, the effect of the differential extinction, works over much larger wavelength ranges than the ones that are involved here. So this is a super popular way of categorizing galaxies, simply because we don't need to worry about choosing the right dust extinction model and knowing that we might get a different result if we choose a different model and so on. We can just not care about that. And what we see in all these points here is hundreds of thousands of galaxies. Each point is a galaxy where they have measured these various line strengths and then placed it in this diagram. And what we can see, these galaxies are from the Slow and Digital Sky Survey, also known as SDSS. There are also similar diagrams for later surveys, such as the Dark Energy Survey and so on. Anyway, this one is fine. And then people have been going to town on these diagrams with various theoretical models and so on, and found out, for example, that anything that is below the dotted curve here, the one that says H2 down here, simply says that physically there cannot be a lot of AGN activity. There cannot be any AGN activity in galaxies here. There's the ionizing radiation is simply not hard enough and so on. Then we see what we call like a composite region here, where there can be some star formation. Oh, so yeah, in the H2 region, basically that means that the ionizing photons must come from star formation. Then up here, we have a region that is completely dominated by AGN. And in here in between, we have a region that is composite. That means it has a contribution from both AGN and star formation. And then finally out here, we have a region that is dominated by shocks due to turbulence, due to accretion, or due to, for example, shocks from supernova explosions inside the galaxy and so on. Although this galaxy also, or this region also contains emission from Seyfert galaxies. So it is a little bit more messy than you could get the idea from just watching this illustration here. But big picture, it is correct. Another thing you can do is that if you are lucky and have some gravitational lensing, and if you have a good IFU, for example, one on NIRSpec on the JWST, you can actually make maps of physical properties. This is a gravitational lens galaxy at redshift 2.4, so that's not super high redshift, but it is still quite high, and it's definitely something we could not do before JWST. This is on scales of a few hundred parsec, out to maybe a couple of kiloparsec that we can see here. And this is the velocity of emission lines. So basically that shows that we have a rotation around here, right? We have a rotation axis that goes something like this. And then we have blue shifted stuff happening here and red shifted stuff happening here. Then we can see the full width of half maximum. We can see that it is rather stable most of the places, apart from these two evil eyes that you can see here. So there's a region where we suddenly have much broader lines than elsewhere, which means that something is depositing a bunch of energy into the ISM there. It is not exactly clear what that is actually, because you can see over here, which is also the same as these contours, this is where the stars are. And you can see that this broad line region here is not where the stars are, and there's definitely no AGN in here either, so it's something else. We can look at H alpha over H beta, which is tracing dust reddening. We can see that the dust reddening of this galaxy is quite smooth again, most of the places, except right here where it is much stronger than elsewhere. So we have like this little really dusty region here, and there's maybe also some elevated dust over here. We have the oxygen 3 over oxygen 2 lines here, which shows us that around this star cluster here, we have strongly elevated ionization compared to in the rest of the galaxy, and so on. This is all the things that you can do with an IFU, and it's really cool. And by the way, this is from my work. This is from a paper I have just submitted this very week to the big scary internet. So yay, go me. One selection function, just to get back to the whole surveys and how to design them thing, one selection function that we use quite often is color selection. This is kind of a cheaper, easier version of a photometric redshift and of an SED. This is what we also call the dropout function or dropout selection, and you can see a very cool illustration of how that works here. This is even a quite old example, actually. I think this is from a paper back in 2003, but it is a method that we're still using. And it is, by the way, a paper by my old master thesis supervisor in Copenhagen, Johan Finbo. What we see is that we have a galaxy, right? And it has what we call the Lyman break here. That's basically where it is either Lyman alpha or the Lyman continuum. It depends a little bit, but it is roughly around 1,000 to 1,100 angstroms that you see this, or between 1,000 and 1,200 angstrom that you see this break. So you can see this is a rather rough redshift determination, but it's very, very effective. So in the U filter, the U band, you can see that there's only a little bit of flux from the galaxy going into this filter. There's quite a lot of flux going into the G filter, which stands for green, U for near ultraviolet. And there's also quite a lot of flux going into the R filter. So if you look at this in imaging as you do below, in the red filter, it is definitely visible, right? You can definitely see it's there. In the green filter, it is even stronger, in perfect agreement with what we see up here. And then in the U filter, it's gone. And as you can see in the filter up here, it's not completely gone, right? But there is very little, and there is so little that it is enough that it can kind of just drown in the general level of noise in this picture. And that is really all we can know, right? If it drowns in the noise, then we don't have a detection, then it is gone for all practical intents and purposes. And so this is a way that has been super effective for finding galaxies at higher redshift. You can, in principle, apply it to any redshift too, right? You could also find galaxies that would drop out between the G and the R bands, for example, or even higher up. The only thing that has kept us from doing that earlier is basically the depth and the sensitivity of our telescopes. Again, JWST has made this much easier, and we have kind of seen again a revival of this dropout technique after the launch of JWST. What you see over here to the right is a way that the researcher, I think that was Chuck Steidel, right? Yeah, I think that was from Steidel, used these filters to find galaxies that were basically these U-band dropouts. And here he basically shows that if you plot their difference in the G and the R bands against the difference in the U and the G bands, then you can take this region up here, and this region will be where you have these U-band dropouts. And then actually these objects are all spectroscopically confirmed. So he has used this not to find new objects, right, but to test that the method actually made sense. And what you can see is that these spectra here shows that these are all galaxies that have redshift somewhere between 2.5 and 3.5, which is exactly what he was looking for. There is some false positives. You can see a little bit of the yellow ones in here. And there's also a few maybe that he has missed. But all in all, it is a very effective way of finding these galaxies at this redshift range. So it has been very successful. But given that we have these Lyman break galaxies, what are they? What is it even that we're looking at when we're finding them? Because of course, when we find these Lyman break galaxies, that means that these are the kind of galaxies that we find at these redshifts. That is both the good and the bad thing about this method at the same time. That the good thing is that you can find a lot of galaxies with it. But the bad thing is that the galaxies you find are all of the same type. And that means that you don't know how many other galaxies there might be out there of different types. But one step at a time, we have to take one step at a time. So in order to understand what LGBs or LBGs were, so these Lyman break galaxies were, people also started to take some follow-up spectra, of course. And then there's this paper here where somebody did what we call a stacking analysis. And that's because originally, back in 2003, these individual galaxies were too faint to get a good spectrum of, right? But if you get spectra of hundreds or sometimes even thousands of these galaxies, and you correct them for their redshift, and then you just add them together, then you will be able to get a picture of what the average Lyman break galaxy looks like. You can't say anything about, or you can't say much about individual galaxy, but you can get a very good picture of what the average LBG looks like And that's what we see in this plot out here. And so we can see that it is dominated by young stars and hot gas. One point, by the way, for those of you who are used to looking at spectra, this is in what we call F nu rather than in F lambda, what we're typically looking at. So if we were looking in F lambda, what we would see for a young star-forming galaxy dominated by the blue is that it would be very bright here, and then it would kind of taper off as we get towards the red. But F nu basically means it is flux density per frequency rather than flux density per wavelength. And that gives us the same physical properties, but it looks different in a plot. And so a typical star-forming galaxy in F lambda will have this like steep drop-off in the ultraviolet continuum, but the same galaxy in F nu will basically have a flat continuum. Anyway, they look different, but we can learn the same things from them as long as we know how to read these plots correctly. And so what we find from this stack of 800 Lyman break galaxies at redshift 3 is that they are dominated by young stars and warm gas, and that they contain a lot of hot stars, strong stellar winds, and so on. So these are very, very similar to the ultraviolet spectra that we have gotten from low redshift starburst galaxies, which tells us that at redshift 3, the typical galaxy, at least as we could observe it with the Lyman break technique, the typical galaxy was a starburst galaxy, or was very similar to what a starburst galaxy in the local universe looks like. So that was a quite important insight, of course. There is still the caveat that we don't know exactly how representative these galaxies are of the general population of redshift 3, but we have found out more about that later on. And so the LBG luminosity function is something that people then went into a lot of work in order to determine. And this is basically us revisiting the Schechter function from before. Remember, it has this, so this is not in flux, but in magnitudes, which means that it has been flipped on the horizontal axis compared to what you saw in the earlier lecture about the Schechter function, right? But basically, apart from that, you can see that it has this power law slope, and then it has this exponential drop off at some point. So that is what it is. And then from then on, it is just a matter of determining what the power law slope is and where the turnover is from the power law to the exponential drop off. And what people have found for LBGs around redshift 2 here is that there is a power law slope of around 2.5. So the faint end slope, which is what we have here, is at the faint end slope, alpha is about 0.5, and then there are many more faint galaxies at high redshift where it is minus 2.5. So you have, that's going to be minus 0.5, sorry. The point is that there are many more faint galaxies at high redshift. The slope here is much steeper towards more faint galaxies, which kind of gives us a problem in the sense that if we integrate this Schechter function with this slope over all luminosities, we will get infinite luminosity. So clearly there needs, sorry, now we can't see for me again. Clearly there needs to be some kind of cutoff both in the low luminosity and in the high luminosity end of this function in order for it to be physical. But as long as we know this, then we also know that there is also a limit to what we actually observe, right? So within the range that we observe, it does make sense. We just need to figure out where and why this low faint end cutoff occurs. Lyman break galaxies also evolve over cosmic time. They don't stay the same at all redshifts. Like the number of them and the luminosity function and so on changes over cosmic time. And one thing you can see for Lyman break galaxies is that from very low redshift, we have 0.1 here, and outwards, the luminosity function grows. Like the overall number of Lyman break galaxies grows quite strongly, actually, between the local universe and redshift around 3. But then something happens at higher redshift from around redshift 4 and towards higher redshifts, yet it actually tapers off again. It becomes fainter again. So from redshift 0 and out to redshift 3, you get a brighter and brighter universe. Well, that's going back in time, but still you get a brighter and brighter universe. But then from redshift 3 to 4 and towards even higher redshift, it actually gets fainter again. This has led to this really important, I think, insight about the cosmic star formation history, which is, I should say, by the way, that what you see here is a extinction corrected and an observed star formation history. These are two different versions of the same star formation history. But that the cosmic star formation history, the star formation history of the entire universe is basically what we're looking at here. And you can see that from the local universe at redshift 0 and out to redshift 3, star formation goes up quite dramatically. This is a logarithmic scale, right? But then once we get to redshift 3-ish, it turns around actually and goes down again so that we have a lower star formation rate density in the really high redshift universe than we have now. And so this period here between redshift 1 and 3, or some people like to define it as between redshift 1.5 and 3.5, or there's no sharp limit, but around this general time around this peak here is what we call cosmic noon, very, very wittily, because originally people talked about this time here, very high redshift, when the first stars started igniting and forming the first galaxies, talked about this as cosmic dawn, right? And then what else to call the time where there's by far the brightest universe and the most stars? Well, we call this cosmic noon. And I guess then in between we have, I don't know, cosmic second breakfast and cosmic elevenses. And today we live in, I don't know, cosmic 5 o'clock tea time or something like that. In any case, cosmic noon is an incredibly important epoch in the history of the universe because this is where by far the majority of all stars currently existing in the universe have formed, including the vast majority of stars in the Milky Way. Another reason why it is so important is that it is the main focus of my research. So you can see, very important. What we have over here in the right side is basically just like a better zoom in of what we see here with some updated data and some better error bars. You can see the error bars here are a good deal smaller than they were over here. But it's basically the same history we see, right? But interestingly, we see that this kind of power law thing that we see between redshift 3 and redshift 8 kind of breaks off and it goes down more rapidly from redshift 8 and down to redshift 10, 11, which is the only place we can, like, this is basically as high as we can get. And this is with JWST data. No, it's not. Sorry, this is what the best we could do with HST before JWST. But it's kind of getting hard to get many more data points here because there simply just aren't that many galaxies that we can even observe here that we can get any kind of useful statistics out of them. One example of the dropout technique is this one that was for a long time the most distant galaxy that we had a confirmed redshift for, called GNZ11, which is called what it is called because it has a redshift of 11. And so what people did there was basically that they observed, as you can see here in the upper left window, right? They observed in a bunch of filters. And where you see these arrows here, these downward pointing arrows, that basically means that's an upper limit. That means that there was a non-detection, and then they take the error bars on the measured flux on that non-detection, and then they say, whatever the flux is, it's definitely not higher than this. It's probably also lower. Might even be a good deal lower. May very well be 0. So you see that there's non-detection, 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 non-detection. Boom! Now there's a detection at around this redshift here, right? And then you see that there are detections all the way out here. And then people went on to say, well, okay, that must mean that we have a Lyman break here, right? And that gives us a redshift of around 11. But as I have also mentioned a little bit earlier, photometric redshifts are notoriously unreliable. We just simply cannot count on them being correct. Often they are correct, but we cannot know for sure. So we need to do some kind of spectroscopic follow-up. Problem with a galaxy like GNZ11 is that it is extremely faint and it is extremely hard to get proper spectroscopy from such a galaxy. Because basically, if you do it in imaging, right, then all the photons that come from a wide wavelength range will all be combined. A wide wavelength range that is all inside the same filter will all be combined into one data point, right? On the other hand, if you do spectroscopy, then they will get chopped up in teeny little slices of wavelength, and each will go into its own pixel. And each of these pixels contributes some noise, which means that you need many, many more hours of observation before you can get a proper signal to noise and actually learn something from these observations. And this is what they could do. This is the best they could do in the era before JWST. You can see you have something here, and then you have something here, and then you can basically fit different synthetic spectra to what you see here and see which one fits best. And they concluded that this fits best. I kind of sort of agree, but it is not super obvious, right? It is messy business when you're pushing the boundary of the faintest things you can see and trying to do proper statistics with really small numbers. It's not easy, and it is quite easy to make mistakes or just draw the wrong conclusion due to bad luck, basically. Of course, again, with the JWST, we can just do this. So this is a galaxy that has been found with JWST at redshift 14. As we can see, JADES GS-Z14. And it didn't take long from JWST was launched till we saw the first spectra of this kind. And you can see that it has so much better signal to noise here. And there's basically absolutely no doubt that this is this kind of dropout and what redshift it is on. You should note, though, right, that there's actually also a foreground galaxy here. So these are kind of important to disentangle, but you can see that this thing that is inside the slit here is not present over here. It's gone. It's a dropout here. It's a dropout here. And then it looks like it's turned up here, right? And then here and here and here it is there. And that basically corresponds to the wavelengths we see here. So with JWST, as soon as we got better gear, as soon as we got more expensive toys, suddenly it was super easy, barely an inconvenience to get this kind of spectra from even higher redshift galaxies. But of course, this was a tiger leap compared to the pre-Hubble era, but we also have quickly hit a wall where we have gotten to where it's not easy to push the boundary even further, and we need to start doing the same kind of things that we previously did with Hubble with JWST data in order to like squeeze the last little few photons out of the highest redshift galaxies, so we can push the record for how distant galaxies we have observed a little bit further. It's definitely still a field where a lot is happening, and it's definitely a field where it is really interesting to follow, like in real time, what is going on. Finally, a look at other survey methods, and those other survey methods, it's generally mainly emission line methods that I talked about before. Basically, we have two main families of methods for finding galaxies, and these are either photometric dropouts or they are emission line galaxies. And we're now going to look at the emission line galaxies and how we do those. So if we want to look for emission lines, there is basically three different strategies we can adopt. First off, there is, if we have, we can do slitless spectroscopy, or we can use an IFU. The problem with an IFU is not impossible. It has been done, and it has been done really efficiently, and people have found a lot of super cool stuff with IFUs, especially with the very large field of view IFU called MUSE on the European Southern Observatory in Chile, but also other IFUs. But using that, you can search a volume in space. You can search so what we look at here is coordinates on the sky, right? We have the right ascension, and we have the declination, alpha and delta, which is basically X and Y coordinates. And then we have the Z, which is the redshift coordinates. And if we use slitless and IFU spectroscopy, we can basically look at a field on the sky, and we can see a quite large spread of redshifts in the same observation. The only problem is that IFUs have small fields of view compared to imaging, so it is kind of inefficient, but it also definitely has its upsides. Slitless spectroscopy is something I'm going to get a little bit back to in the end. It has not been super popular for a while, but again, with the launch of JWST, it has gotten a little bit of a revival and gotten more popular again. Long slit spectroscopy is good in the sense that you can get a lot of information. You can get a lot of information about a particular object, but it is not very good for surveys, like for searching big areas of the sky, because as you can see, the area that it actually searches is really, really small. So that one is out. We're not using that for surveys. Finally, we can use narrowband imaging, as I talked about before, where you use a narrowband, and for that narrowband, you can search a large area of the sky, but only in a rather small redshift range for galaxies that have emission lines in this particular redshift range. But what you can then do, of course, is that you can use multiple narrowbands, and that way build up and search through a rather large volume of space anyway, if you just have multiple filters. So this is a quite effective way of doing it, and has historically been, I think, the most popular and the most efficient way of finding many high redshift galaxies. In particular, it has helped us find a lot of so-called Lyman alpha emitters. Lyman alpha emitters are galaxies that emit, well, Lyman alpha. If you look at a galaxy, or rather a simplified toy model of a galaxy that has a bunch of really hot stars in the center, and then an envelope of neutral hydrogen surrounding it, then every ionizing photon is absorbed by a hydrogen atom, and it is ionized, and that creates an H2 region, and it creates some strong line emission. The way that works is that all the photons that are absorbed above the 912, or rather below the 912 angstrom wavelength, basically this is, okay, let me take a step back. So here we have in frequency space, right? here we have a black body spectrum. This is just a very simple toy model of a galaxy spectrum. But you can see that we get higher and higher energy as we go towards the right on the x-axis here. And at some point right here at 912 angstrom, we reach the limit where they have enough energy to ionize hydrogen, neutral hydrogen. And that means that all the photons inside this purple area here are absorbed by the gas. What then happens is that the gas recombines and gives rise to a series of emission lines. And that means that about 2/3 of all the energy inside this area here, this integrated range of the spectrum, ends up in this one very, very narrow and often very, very bright emission line at 1216 angstroms, called the Lyman alpha line. Sorry, 2/3 of the ionizing photons, but actually only 1/3 of the ionizing energy, because they have different changing energy dependent probabilities of interaction. But still, a very, very large amount of energy gets concentrated into this one very narrow, very bright emission line. And that is perfect for looking for galaxies at high redshift. Because if you have an emission line and if you have a narrowband filter that happens to fit that emission line at a given redshift, like we see here, right? Then you can see, basically what you can see here, the red stuff, that is a very simplified spectrum where you have a very, very faint continuum from the stars, and then boom, you have the Lyman alpha line, and then you have very, very faint continuum from the stars again. Like in the broadband, you might get some emission, but it's not a lot, because you can add up a lot of this here, but there isn't really a lot of flux. There isn't so much integrated flux in the Lyman alpha line either, right? If you take the G filter here, and then you take all these photons from this line, they will get spread out over the entire filter if you use the broad filter. And that means that basically the same area, but spread out over this width here, means that basically there's nothing to be observed. On the other hand, if you have a filter that only sits right around the line, then there will be no noise from these surrounding wavelength ranges here. So all you will see is a very clean, very high signal to noise signal from this Lyman alpha line in this very, very narrow filter. And that's what we see over here on the right side. Here you have the narrow band filter where you see Lyman alpha very clearly. And here you have the U band where maybe there's something. It's hard to see if this is just noise or if it's real, right? You can't really see that from this kind of observations here. It's a coin toss whether this is real or not. This is absolutely real. This is absolutely real too. But this one, we don't really know. But then again, look at the narrowband and boom, absolutely no doubt that there's definitely a detection here. So this is giving really good signal to noise. It's getting really high confidence detections and very precise redshift determination, but the filter needs to match the redshift of the Lyman alpha line very closely. It can only find Lyman alpha lines in a very narrow range of redshifts. But again, if you have a large array or a large battery of narrowband filters, then you can still, over multiple observations, build up a rather impressive catalog of emission line galaxies that way. And that has for many years been kind of the bread and butter of how we have found galaxies at high redshift, even out to redshift where we might not have been able to see so many Lyman break galaxies. And another thing that is good about this is that this method can be used to find galaxies that don't have a lot of continuum, right? If we go back and look at the Lyman break galaxies, all the way back here. We are relying on these galaxies having a rather strong continuum, which means that they need to be rather massive, and they need to have a rather strong star formation going on. Now, in order for the Lyman alpha to be observed, you also need rather strong star formation, but you don't have to have a very strong continuum emission. So you can find much lower mass galaxies, much lower luminosity galaxies with this method than you can with the Lyman break method, which means that you can sample the part of the luminosity function and the mass function at these redshifts that you can't really get with the Lyman break galaxies. So these are also very good methods for complementing each other to get a complete image of what the stellar mass function, the stellar luminosity, or the galaxy luminosity function looks like at a given redshift range. And just an example here, because this example was a very neat and pretty example that is very good for learning how to understand the method, but often in practice, it doesn't look as pretty, it doesn't look as neat. And here we have an example where it's way more messy, right? You can see that here we have the narrow band filter, and we have something that it looks like a detection, but it is not something that will just jump to your eyes as soon as you look at it, just from looking at it, right? You will need some kind of very systematic, very specific search techniques or algorithms, or just a lot of patience to find this little dropout here between the narrow and the broadband filter. And sometimes you can't really know if it's just noise or if it is real. So it is not always as neat and as pretty as in the textbook example, but it's a very, very important and a very effective way of finding galaxies at high redshifts. The Lyman alpha luminosity function is something else that is very interesting. It is basically like the typical luminosity function, but just from Lyman alpha emission line luminosity rather than galaxy luminosity. And there are some really funky things going on in these figures here. I don't want to get too much into depth about what they mean, but basically you can see the luminosity function and various redshift ranges here. And one thing you can see is, if you look at this figure over here in the lower right, is that you can see that the Lyman alpha luminosity function, that basically the strength of the Lyman alpha line compared to the light that you get from the star, from the galaxy in itself, goes up over cosmic time from redshift 2 to around redshift 5 or 6-ish. But then around redshift 5.5 to 6, it turns around and it actually drops. And this is a relatively old paper, at 2018. We have got even more of these measurements afterwards, and it is definitely true. It is even stronger now if you look at newer, more current plots. The Lyman alpha luminosity function takes a nosedive here around redshift 6 and to higher redshift. And that's simply because this is where we hit the wall where the universe, the intergalactic medium, is no longer ionized. And when the intergalactic medium is not ionized, then Lyman alpha gets absorbed by neutral hydrogen. Lyman alpha gets very, very effectively absorbed by neutral hydrogen. So you basically don't see Lyman alpha at redshift higher than 6 or 7, because the IGM, the intergalactic medium, is neutral at this point. And this is actually one of the most effective ways we have had to mark when the universe changed from being largely neutral to being largely ionized. Or rather, I should say, this is not exactly where it changed. This is the end of the period that we call the epoch of reionization, which started much earlier, around redshift 20. But this is when the universe, the cosmic percentage of of hydrogen atoms that were ionized got so high that it became transparent to Lyman alpha lines, which is like 1 in 1,000 neutral atoms that you can have. You can have about a neutral fraction of 1 in 1,000, and you can still have a universe that is relatively transparent to Lyman alpha. Much higher than that, and then it becomes opaque and you can't see a lot. This also comes with a bunch of caveats because there are still ionized bubbles inside the earlier neutral universe, and if these bubbles are large enough that the Lyman alpha line can redshift out of resonance with the hydrogen atoms, then they can still escape, and so on and so forth. But that is a little bit too much for the scope of this course to get into in depth. So I will leave it at this. But take home point from this plot is Lyman alpha gets stronger and stronger as we go back in time, reflecting a higher and higher ionized stage and higher star formation activity in each galaxy, until you reach this point here where the universe is actually not ionized anymore and therefore becomes opaque to Lyman alpha, and the luminosity function drops rapidly and dramatically over a very short redshift range. And again, this is basically how we could pinpoint the so-called end of the epoch of reionization. Like, this is when the universe became transparent to Lyman alpha. This is officially where the epoch of reionization ended. And if you are still with me after a rather long lecture here, there is one slide left, which is that I promised to get back to you about slitless spectroscopy. Because slitless spectroscopy is a really, really efficient way of discovering emission line galaxies, even more efficient than narrowband imaging if you have spectrographs that are that have large enough field of view and high enough sensitivity and so on. And for a long time, that was kind of hard to do. It's difficult to do from the ground because we often look at very small objects and they get smeared by the atmosphere and so on. And so we could basically only do it with the Hubble Space Telescope before. And the Hubble Space Telescope only had a mirror of 2.5 meters, and its optics and its electronics were not very well attuned to infrared light. It was kind of something that was an afterthought in the design of Hubble. Now, James Webb Space Telescope, on the other hand, was from the get-go designed to be an infrared telescope, which means that it was designed to do exactly this, find large populations of galaxies at very high redshifts. So it is absolutely brilliant at this, and that means, again, that this technique has gotten a revival with JWST. So how does slitless spectroscopy work? So instead of putting a slit, or instead of doing like a spectrum for each pixel as an IFU would do, what you basically do is that you just take the light and you send it through a prism, and that spreads it out. And that means that each of these things you see here is a galaxy, and it is a spectrum, but it is a very, very low resolution spectrum. Low resolution in terms of spectral resolution. But what you can see is you can see the general spectral shape of a galaxy. You can see if there is a Lyman break, for example, and you can see if there is an emission line, which will show up as a little single dot at some point. And what you do then is that you take massive amounts of spectra like this, just in one go, just in one pointing, and then at the same time or immediately after, you also take an image. And then you have a calibration where you know that a galaxy at zero redshift will have its Lyman break showing up at this distance from the image, and it will have its, its oxygen 3 emission line showing up at this distance from the image, and so on. And then knowing that, you can basically see that the larger the actual observed distance is from the calibration distance at 0 redshift, the higher the redshift of the object is. So this is a way of finding like high redshift objects or objects at any given redshift range at basically at an industrial scale. And it is also a way that means that you can find rather faint objects because the spectral resolution is so low that your signal to noise gets almost as good as it would be with imaging. But unlike with imaging or unlike with an SED, you actually get a very reliable redshift determination of an object this way. You can't learn a lot else than the redshift from slitless spectroscopy, though. I mean, you can learn a little bit, but typically not a lot. So this is mainly a method that we use to find and flag interesting objects for follow-up observations, objects that we want to learn more about. This is a particular observation with the JWST slitless spectrograph called NIRIS. And these are observations and images that are made by our former postdoc here at Stockholm University, Axel Runholm. But it is definitely a technique that has become very popular again after the launch of JWST. Okay, this was a long one, so now we only have left the discussion questions, and let us just savor for a moment that these are the last discussion questions you will have to think of in this course. These are the last discussion questions that you will be going through in the first Galaxies course as Stockholm University. And who knows if any of the other courses after this have this kind of discussion questions. So you should really take your time and savor these discussion questions. Okay? Great. First discussion question is, the photometric redshift technique works quite well at redshifts below 1. Why do you think it might fail at higher redshift? Because I didn't actually say that, but yeah, photometric redshifts are very good at low redshifts, but they become more and more unreliable at higher redshifts. Why is this, do you think? And let's say you only have telescope time to observe in, say, 2 filters in imaging. How would you design an experiment to detect galaxies at redshift 3 or higher? Second question is, why do you think the cosmic star formation density evolution seemingly drops at high redshift? Try to give a physical explanation of why that would happen, but also consider if it is even something that actually happens, or it could be some kind of observational effect that kind of like an optical illusion, you could say, that made us think that it is like that, but it's just because we don't see the full image because of some kind of observational effect. That was it. That was the last lecture of this course. Thank you so much for staying with me this far. And I mean it this time because this was a rather long lecture, but I didn't feel like chopping this one up. So here we are. I hope you availed yourself of the pause button if you so felt like. And thank you for now. I will see you in the classroom. Bye-bye.